Hi everyone, I'm just going to walk you through the virtual assignment for this week. So we were going to do it together in the lab, but we have a snow day. So you can watch this YouTube video. It will walk you through a protein assay called the BIO273 assay. So you'll see 5 standards that have been prepared, and those will be measured, the absorbance will be measured using the spectrophotometer. You guys are going to record in the table %T and calculate absorbance using 2 minus log of %T. So you'll notice that he begins with the blank. So you're going to start with the blank as 100% T and then record the %T for each of those standards. Okay, then he'll show the %T for the unknowns. After you collect the data in the table, you're going to calculate absorbance, and then you're going to create a graph that's called a standard curve, where concentration is on the x-axis and absorbance is on the y-axis. Okay? So part of this exercise is practicing graphing data. So once you have your data, here, you need to make a graph. So when you're making your graph, make sure your x-axis is concentration. And so our concentration here runs from 0 up until 10 milligrams per mil. So when you're making your x-axis, don't be deceived by all of the values that you have. It's not important that you have a line for 0.625 and a line for 1.25, because that might not end up creating a nice axis for you. So what you should do is just look at your highest value. Okay, our highest concentration is 10. So my x-axis needs to go from 0 to 10. So all we have to do is evenly space it. It would make sense to go up by 1, 2, 3, 4, 5, all the way up until we get to 10, okay? And just make sure that all those ticks are evenly spaced on your x-axis, okay? Same thing for absorbance on your y-axis. I'm not going to be influenced by the specific values that I have collected. I'm going to look at the highest one. It's 0.47, and I'm going to round it up to 0.5. So if I know that the highest point on my y-axis is going to be 0.5, I can reasonably break that down and go up by 0.1. 0.1, 0.2, 0.3, 0.4, 0.5. And I can use as many boxes as I want to represent each of those values just to make it fit. Okay? It could be 3 boxes, it could be 4 boxes, it could be 5 boxes for every increment that you go up. Okay? As long as you have a nice even scale that's easy to read, then you're going to be able to find these points in between your data points a lot more easily than if you have weird decimal numbers on your scale. Okay? When you're making your graph, you're going to put a very nice title on the top of it. So make sure, like we wrote on the board last week, your title must include the type or the name of the graph. So this is like an absorption spectrum or a standard curve. The name of the analyte. So for this one, we are measuring BSA, bovine serum albumin, the protein. The concentration range of the data should be in there. For this particular graph, because we're doing a BIO273 assay, we should include the name of the assay in the title. And then the information we need from our measurements. So our instrument used was the Genesis 30 spectrophotometer, and all of these absorbances were measured at a particular wavelength, which was determined in the video. So if you didn't write it down, go back and check what the Amax was that was used to measure all of these absorbance readings. Okay? When you're done, you should have nice linear points, and you can use a ruler to draw a line of best fit. Okay, that was not a good job, but you're going to use a ruler and make a nice straight line that goes through those points. When you do part B, the Bradford assay, you're going to do the same thing, a new video link, you have new concentration values. Again, you're going to collect %T and determine the absorbance. What's going to happen for your Bradford assay graph is that you're going to find that your points are not linear. So the first few points of your graph will be linear, and then what you'll notice is that they begin to plateau. So this is something that happens when we reach the upper sensitivity range of the assay that we are doing. So once our solutions get too concentrated, they're too dark, and we can't really detect a difference between their concentration by color, and so neither can the spectrophotometer. So when you're making this graph, you're going to use a ruler for as much of the graph as you possibly can. Okay, so you're going to do your line of best fit and use a ruler to go through as many points as possible. So then what you'll notice is you'll reach a point where your points end up below, your data points are below the line of best fit that you've been using. And so then you're going to switch to something that is called a French curve. We have them in the lab. So a French curve, if you can see here, is a nice smooth surface that has a curved edge. And so what you would do is put this right onto your paper where your points start to plateau, and you try and follow the shape of the data and create a curve that matches those points. So if you don't have something at home that you can use to create the curve, you can wait and do it in the lab, or you can just try and sketch it by hand. So if I was going to do that, I would say start from my last point that is on the linear portion of my graph, and then try to curve my line towards, probably do a better job there, curve my line towards the other two data points, okay? And then of course I have too many lines there, I need to straighten that out and make it look nice. So the idea is this is real data, it is reliable, we made our solutions properly, it's not a mistake. And when we do a line of best fit, we're trying to show the pattern that the data points are following. So we don't want to put a line up here because that's not where the data points are going. So we want to follow along that line. That way, if we have an unknown that gives us an absorbance somewhere in that area, I can be sure that I am estimating it appropriately for the data that I have and not using this straight line. You can see the difference in concentration that I would estimate, whether I use the French curve line or the straight line, is quite different at that absorbance reading. So we want to make sure that it matches the data we've collected as closely as possible, okay? So this would be the right one over here, and this would be the wrong one. We don't want to follow along that linear line because this is not what our data is showing us, okay? Shows us that around this absorbance height, the graph is plateauing, right? We have this point here as proof of that. Okay, so you guys can go ahead and complete those graphs. Make sure when you're showing the interpolation of your unknown, you indicate the unknown absorbance on the y-axis. You indicate the concentration that you are estimating on and include units. And those dotted lines should be drawn in as well. Make sure you're using a ruler for those dotted lines so that they are perfectly horizontal and perfectly vertical on your graph, okay? When you're done, you can scan and submit your graphs in Blackboard.